Let's discuss inference rules. Among the connectives, the implication plays a crucial role in inference. Let's see first its different variants and also clarify the terminology. So first of all, an implication is a Boolean expression or actually a proposition of the form P implies Q. So sometimes you would see it written as P implies Q, but this is the same. Okay, so we call also converse the implication. That goes from the right hand side to the left hand side. Q implies P. And also the contrapositive is the negation of the consequent or the right hand side, not Q implies not P. We call the inverse if you take the negation of the first side of the left hand side implies the negation of the right hand side. It's important to observe here that some of these are equivalent and some are not. So for example, we have seen in the previous slides that we could write actually P implies Q is logically equivalent to not Q implies not P. So we can prove this easily by doing some truth table. So we have P implies Q, not P, and P implies Q. If you know the truth table to prove that these two expressions are logically equivalent, we are going to put the possible values for P and Q truth values. So false, true, and false, false. So just to iterate on the truth values of the implication is false only when we have true implies false. When we have true implies false, then we have false value of P implies Q. So it's going to be here false, and for the rest it's true. Okay, so not Q implies not P would be not Q, where you are going to negate this element here and this element here. Not Q implies not P. So let's take an example. Hot is a sufficient condition for my going to the beach. If it is hot, then I go to the beach. The converse of this proposition is implies P, which means that I'm going. To take the right hand side and put it on the left hand side, and again I put the left hand side on the right hand side, beach implies hot. The contrapositive of this implication here is, which is equivalent to hot implies beach, would be not beach implies not hot. While the inverse, which would be the contrapositive of the converse, would be actually not hot implies not beach. And again, these two elements are actually logically equivalent. All right, so we see how we could use this definition of implication of contrapositive to actually do inference based on some inference rules. Now let's discuss some inference rules. Our first inference rule is called modus ponens, which shows how to infer or how to drive logically new sentences from existing ones. So for example, if we have P is true, when we write P by itself, which means that if P is true and if P plus Q is true, then we can infer or make a logical deduction that actually Q is true. So this one here stands for inference. This is an inference with the modus ponens MP, all right. So if I observe P and Q is true, and if I have P implies Q is true, then I can confidently infer that Q is also true. So how can you write this actually as a Boolean expression, because here we are not used to write this line of inference. But in fact, you can find it easily as an implication. So this means that there is an implication this way. So we could write this Boolean expression as P if I have P and I observe P implies Q. So this means that if these two elements are true, then I can confidently imply that actually Q is true. As a matter of fact, if you write the truth table for PQ and this expression, so if you do the truth table, you will find that it is actually a tautology. So it's always true that if you have P true and you have P implies Q true, the conjunction would imply that Q is also true. And warm plus sunny is true. The sunny is true, and this is coming from simply the definition of implication itself. We let the implication warm implies sunny is actually cannot be true if the left hand side is true and the right hand side is false. So the only way where this implication is false, and when we have true implies false, given that this part is true and the whole implication is true, it means that we must have that sunny is also true. So this is a very powerful inference mechanism that we can use and reuse when we have a knowledge base to drive new sentences and make inferences about the two. Modus ponens can be extended by handling what we call horn clauses. It is proposition of form P1 and P2 and Pn implies Q. So now on the left hand side, we don't have only one single proposition. We had a conjunction of propositions. Modus ponens deals with horn clause is as follows. So we are going to just extend it. Instead of having just P and Q implies Q, now we have if P1 is true, P2 is true, Pn is true, and if we have P1 and P2 and Pn implies Q, then we can confidently infer Q. So this is just a way to say it is a marginal fashion that if all these elements are true, then we know that their conjunction is true. If the implication is true, then we can infer that Q is also true. Another variant ponens is called the modus tollens. So in modus tollens, we are going to leverage the fact that an implication P implies Q is logically equivalent to its contrapositive. Not Q implies not P. So this is the key idea of modus tollens. So we have P implies Q is equivalent to not Q implies not P. So if we have this, then we have P implies Q and we observe not Q. So look at the rules. So if we observe not Q, so if we observe not Q by modus tollens, which is actually applying this contrapositive, we can infer not P. So not P and P implies Q would infer not P. So this is just so we could rewrite that is not Q implies not P. You could, if you were to rewrite this one, then you could see that by modus ponens, not Q and not Q implies not P would need to not P, but if we rewrite just as P implies Q, we call this modus tollens. This is pretty powerful as well. So in case we want to infer not the negation of proposition, we could use modus tollens as an inference tool. As an example, if we consider again this example, hot implies beach. So probably this implication could be used along with hot. If I observe that it's hot, I could infer for sure that I'm going to go to the beach. This is what I do always when it's hot. Now, if I want to use it another way, hot implies beach, which is not beach implies not hot. So I'm going to use the fact that if it is not, if I don't go to the beach, then it means that if I'm not, if I don't go to the beach, then it means that it's not hot. And if I observe that I didn't go to the beach, and then I could infer that it's not hot. So you could say that we could do inference with these two aspects of implication, which is pretty powerful. The one is called modus tollens and this one is called modus ponens. When we do inference, we can also use a set of all the common rules, and this is includes what you call addition. Addition means that you are using the connective of disjunction. So if we have two propositions P and Q, so the addition means that if P is true, then you can add to it anything. If P is true, then by definition of the disjunction, P or anything else is also true because one of them must be true. So P infers P or Q. The rule of simplification is by removing one of the proposition from a conjunction. So if we know by definition of the conjunction that P and Q is true, then any of these elements of the proposition in the conjunction is also true. So if P and Q is true, then you could infer that Q is also true. And you could also have P and Q is true, you could also infer that P is true. So a conjunction of literals can actually infer the truthfulness of any of the literals in the formula. We talk disjunctive syllogism. This is RQ and not P. So if P of Q is true and we have not P is true, mean that P is false, then P or Q is actually false, RQ, which is will actually we will leave it up to Q. So if the truth value of this expression would be simply Q, so If P or Q is true, then one of them must be true. And we know that P is false, then it would depends on Q. So it could simply these two elements here and infer that it would depends on Q. And finally, what we call a hypothetically syllogism is syllogism in which we have if P implies Q and Q implies R, it's kind of transitivity. Given that these rules are actually 100% sure, then we have P plus Q is true, Q implies R is true. Then we must have that P implies R is also true. So these are all useful rules when we do inference to derive new sentences from the launch to make launch base to make actually new sentences. Let's discuss this table and summarize all these inference rules. This table now summarizes the different connectives. So we have P and Q atomic propositions. On the left hand side, separated by double lines, with a set of compound propositions. So we have the negation of the proposition, the conjunction of the disjunction, and double implication are if and only if. All right, so we have a truth table of size 2 to the 2, which is the number of proposition which would be 4 lines in truth table. Just to clarify the terminology of the implication, so we have P implies Q is the implication, so we need sometimes refer to the left hand sides and the right hand side. So we call this left hand side, this part right hand sides. Sometimes you are also here talking about the premise and conclusion, are also the body and the head are condition, conclusion and conclusion. This is different terms to refer to the left hand side and the right hand sides of the implication. So we see later how we use truth table to make proofs.